In the last section, we talked about molecules, and a molecule as being a representation of two atoms joined together. And we said that elements generally tend to be joined together as molecule form. What we'll look at in this chapter is dealing with, or this section is dealing with chemical formulas. And chemical formulas come in many different forms and a variety. A chemical formula is a representation of the composition of a molecule in an ionic compound or a molecular compound. And we'll talk about the difference between those in this section. A chemical formula represents what is joined together in a molecule for the most part. Now, again, we're going to start off talking about what are called molecular compounds. A molecular compound is a combination of two or more nonmetals. And molecular compounds are very common. Nitrogen dioxide, carbon dioxide are some examples of molecular compounds. Now, when we represent molecular compounds or ionic compounds, there's a different ways we can represent them. For example, what you see here is a chemical formula for the substance sucrose or sugar, C12H22O11. And in that, we can see again that there are 12 carbons, 22 hydrogens, and 11 oxygens in one molecule. So again, that is representation of one molecule of the compound. Now, most molecular compounds that we encounter are, again, only nonmetals. We see nonmetal and nonmetal combined. Now, what we represent them in the formula we see a lot of times is called the molecular formula. A molecular formula is called is a representation of what is actually happening in the compound. It tells you exactly how many of each element are in the compound. So, for example, molecular formula for sugar up there is C12H22O11. It tells us exactly in one molecule there are 12 carbons, 22 hydrogens, and 11 oxygens. Molecular formulas give you actual numbers and amounts of each type. All right, that's the one that's most commonly used. Now, there are two other types of compounds or formulas that we use as well. Some other examples of molecular formulas: hydrogen peroxide, which is found in your medicine cabinet, H2O2, has 2 hydrogens, 2 oxygens. Ethylene has 2 carbons, 4 hydrogens. Those are molecular formulas. Another type of formula we use frequently is called an empirical formula, and an empirical formula does not give us quite as much. It only gives us the simplest whole number ratio of the atoms in a molecule. Now, you might be asking yourself, why would we use that? And the reason is because empirical formulas are the simplest form that we can get. In experimental studies, we can determine empirical formulas quite easily. They are what can be determined first. So even though they give us the least amount of information, they are the things that can be easiest to determine. We'll see as we go into Chapter 3 how we do that. For example, we just said they are the simplest whole number ratio of the atoms in a molecule. So hydrogen peroxide had a molecular formula of H2O2. Its empirical formula is just HO. It is a reduced down form of the molecular formula. So the way you can tell if something is an empirical formula is if it's been reduced to its lowest forms possible. Ethylene had a molecular formula of C2H4. Its empirical formula is CH2. Again, it has been reduced to its lowest form. Now, there are some compounds in which their empirical formula and molecular formula are the same thing. So the molecular formula, again, which represents exactly what is in one molecule of the compound, and its empirical formula, the reduced ratio, is the same thing. Sugar that we saw above was an example of that. Sugar has a molecular formula of C12H22O11. It is also an empirical formula because there is nothing we can factor out of all three of those terms to make it reduce down any further. So molecular formulas and empirical formulas are the first of the two. Again, empirical formula, if you're thinking of good, better, best, an empirical formula is good because it gives us a ratio and it's easy to determine experimentally. Molecular formula is a little bit better. It tells us additional information. It tells us exactly how much is in one molecule. Now, the last of those is called a structural formula. A structural formula is the best of the three. The structural formula tells us not only what molecules or what atoms are in the molecule, but it tells us how they are arranged and how they are attached to one another. And that makes a very big difference to us in the chemical world. Methane, for example, has an empirical formula and a molecular formula of CH4. However, its structural formula tells us or shows us that carbon's in the center and 4 hydrogens are attached to that. Now, why is it important to have this? Well, let's look at a specific example where they distinctly come in different. I have 2 compounds. Both have the chemical formula C2H6. All right? That is the empirical formula, that is the molecular formula. So in both cases, that is those substances. Now both these substances, even though they have the same empirical formula, they have the same molecular formula, are distinctly different. One of these substances is highly poisonous, and even drinking it in a small amount will kill you. Breathing it or smelling its fumes in a very small amount will knock you out. The other is totally safe to drink in certain quantities, up to a certain amount, but again, drinking in large quantities will be poisonous to you. Now, if we look at the empirical molecular formula, it doesn't tell you a whole lot. If I look at the structural formula of these two different things, we start to see a difference. The first structure looks like this. And you can see that we have two carbons joined together, and then an oxygen on the end of the chain of carbons, and a hydrogen attached to that. The second structure looks like this. And the difference is that the carbon, or the hydrogen, I should say, is in the middle of the two carbons, giving me a totally different structure. So even though these two things are empirically the same and molecularly the same, they are different structural formulas. Now, you might be saying, so what? What's the big difference between these two? There's a huge difference. This is ethanol. Ethanol is the alcohols in alcoholic beverages, and anybody who's 21 years of age and older can tell you that you can drink those in certain amounts. However, every year across the country, there are thousands of college students who die from alcohol poisoning because they drink too much for their body and their body cannot dispose of it. So it can be poisonous, but when drank in moderation, it's fine. The second substance is ether. Ether used to be used as an anesthetic in Civil War or in surgeries, but if you drank it even the smallest amount, it is highly poisonous. So these two substances, you can see clearly that you can have two substances that have the same empirical formulas, same molecular formulas, but different structural formulas, be vastly different. Empirical formulas, again, are just a ratio of elements in the compound. Molecular formulas, again, are exact numbers, and structural formula tells exact numbers and how they're arranged, the best of the three. All right, so those are dealing with molecular compounds and how we represent them. The second type of compound we're looking at then is called an ionic compound. And ionic compounds are very similar in how they behave, but the ionic compound is slight difference in what we have. An ionic compound is a combination of a metal and a non-metal. Most frequently, we refer to these throughout the course of the year as another term. The term we will synonymously use for that is called a salt. Now, I know you hear the word salt and you think about table salt. Table salt is just one of several types of salt. Any ionic compound is classified as a salt. That is a broad classification. Now again, ionic compounds begin with a metal, they end with a non-metal or a polyatomic ion. All right, so it's either metal and a non-metal, metal and a polyatomic ion, or ammonium, which is one of your polyatomic ions, and one of those two things. The difference between an ionic compound and a molecular compound is that ionic compounds always exist as an empirical formula. They will never exist as a molecular formula or a structural formula. They are always reduced to the lowest whole number ratio. Now, the way we figure out what they're going to be is that we use the charges on the periodic table. Now, to figure out the charge on the periodic table of elements, you need to get your periodic table out and refer to this drawing. So if we look at your periodic table, when you're looking at it, we can tell most elements their charge by looking at the periodic table. Now, the numbers that we refer to, again, are charge, not oxidation number. Later we'll talk about the difference between those two terms, but on the periodic table it is expressed for you. The alkali metals in the first family are all +1s. That means everything down through here, when they form ions, they form a +1 charge always. The alkaline earth metals down through here all form a +2 charge. We're going to skip over the transition metals for right now. We're going to skip to boron and aluminum. Boron and aluminum and gallium and indium down through here all have a +3 charge. Again, we're going to skip over carbon, silicon, germanium, and we'll talk why that is a little bit later in the year. We go to nitrogen. Nitrogen and down all have a -3 charge. The chalcogens, oxygen and below, all have a -2 charge. The halogens all have a -1 charge. And the noble gases have a 0 charge. They do not form ions at all, therefore they never take on a charge. Now the transition metals are a little more complex. For the transition metals, we need to zoom in and look at them a little bit more. For the transition metals, the numbers we're going to refer to are the numbers right here above the symbol. And you can see them the same for everywhere. Now when you look at the numbers, you notice something very unique about them. Titanium, for example, has the numbers 4, 3, and 2 right there. And it's sort of odd to most students that they're not listed in numerical order of 2, 3, and 4. Now, if you look a little more closely, you'll notice that 4 is bold compared to the other 3. Those numbers are the charges they can have. Now, transition metals are unique because they can have more than one possible charge. So in this case, titanium can be +4, it can be +3, it can be +2. That's why they're called transition metals. They can transition their charge from one form to another. +4, since it's bold, is the most common one. So therefore, from here on out, if you're asked to write a formula or determine the charge of a metal, and you are not given a specific case, you should use the most common charge. So titanium is +4. Now, if you look at iron, for example, iron has two numbers, 3 and 2, and you'll notice they're both bold, and then 6 is out there, and it really is neglectful. 3 and 2 are both bold, which means they're both common charges of iron. However, in this situation, since 3 comes first, we know that 3 is the more common of the two. All right, so for transition metals only, do not use this for any other elements. The alkali metals, alkaline earth metals would be okay, but definitely not the non-metals. Those numbers are how you determine the charge of the elements. Therefore, if I said copper on a test, and you're using it to write a formula, you should look at copper and copper as 2. If I say copper 2, then I'm telling you specifically that I'm using the copper +2 charge. All right, so if we go back to our notes now, how do we use this and what's this useful for? We use those to help determine what formula is going to form as a result of two compounds, two elements reacting together. For example, aluminum tends to be +3, oxygen is -2. When they combine, the goal of forming an ionic compound is their charges will add to 0. So they combine in a ratio that the two charges add to 0. So for example, aluminum is +3, oxygen is -2. What I do is called the least common multiple method. The least common multiple of 3 and 2 is 6. So in order to have a +6 charge of aluminum, I would need 2 aluminums. In order to have a -6 charge to balance out those charges to add 0, I need to have 3 of them. So it's O3. So we have Al2O3. Now another method we use is what's called the crossover method, and that's what's being demonstrated here. In the crossover method, what we do is we take the number only, not the charge, of the aluminum, and we bring it down with the oxygen. We take the number only of the oxygen and we bring it down with the aluminum. We then write those two things together with those numbers as subscripts, and that is the formula for the compound. There are two situations where this does not work. The two situations where that does not work is, in this example, if I have aluminum, let's say, +3, and I had nitrogen -3. In a situation where the two charges are opposite and equal, like they are in this case, we simply ignore the charges and we put the two elements together. So if I have aluminum +3 reacting with nitrogen -3, the compound that's going to form is going to be AlN. We ignore the charges. I do not write it as Al3N3. The other situation where it does not work is when the charges can be reduced. For example, Pb +4 O -2. In this case, when I look at the two charges, I do not just bring the 2 down with the Pb, the O down with the 4 down with the O, and write the formula. Before you do that, you would need to reduce the charges. So in this case, if I reduce the charges, I reduce them to +2 and -1. So Pb +2 is reduced, O minus 1. Now I do the crossover method, and I'm left with PbO2 as my formula. All right, so seeing that example, we're going to do several practice problems in determining the charge or the formulas of the ionic compound that would result. You would need your periodic table. I will never expect you to memorize those charges. However, as time goes by, you will start to use them more and more, and you will start to learn them. For example, sodium. On our periodic table, we look, and if we determine the charge of sodium, we find that it is +1. We find oxygen, and we find that it is -2. When I do my crossover method, the 1 comes down, the 2 comes down. Our formula that is produced is Na2O. So when sodium and oxygen combine, that's the formula that would result. Our next example, aluminum is +3. Chlorine is -1. When they combine, I would get AlCl3. Again, the number comes down as a subscript. Please do not leave it up in the coefficient form or as an exponent. In the next example, magnesium is +2, phosphorus is -3. When I combine them to write an ionic formula, I would get Mg3P2. So when we're combining elements, we simply just cross them over. Now, we also have to do ionic compounds, as I said, with polyatomic ions. For example, if I have calcium and sulfate combining, calcium is +2. I can learn that from the periodic table. Sulfate, SO4, is from your polyatomic ion list, which you have to have memorized, or you should try to memorize those, is -2. It is a very time-saving effort to do that. If not, you will not have time to figure out everything you need on the tests. So calcium +2, sulfate -2. Again, charges are opposite and equal. I can ignore those and just put them together. Now, when I have a situation like calcium +2 and nitrate -1, in this situation, I have a polyatomic ion and a metal. Again, I cross over. The 2 is going to come down here. The 1 is going to come down here. When I put them together, Ca is 1. And to express the fact that I have 2 nitrates, anytime I bring a number down with a polyatomic ion, I must put the polyatomic ion in parentheses first. So when that 2 is coming down, I have to put the parentheses around the 2, around the NO3, and show 2. What that is showing is I have 2 of that entire particle. If I didn't do that, I would have something that looked like this, and that gets confusing. Or I see students do this. And that is not possible either. Now, the other question I commonly get asked is, can I just distribute that number through? And the answer is no. CaN2O6 is also not acceptable. So these are not acceptable forms. Nitrate is one particle. We need to treat it as such, and therefore we keep it with the number outside. So anytime you bring down a polyatomic ion, charged polyatomic ion, you simply leave it as is and put parentheses around it. If I have another example, I have ammonium, which is a +1 charge from your polyatomic ion list, and if I were combining that with carbonate, CO3 -2, I have this combination. The 1 is going to come down with the carbonate, so since it's a 1, I don't need to put parentheses. I do not put parentheses when there's a 1. It is not necessary. The 2 is going to come down with the ammonium. Since ammonium is a polyatomic ion, I start by putting that in parentheses, NH4, and then I bring the 2 outside of it. The CO3 then comes after. So we have NH4, 2, CO3. This is a wrap-up then of looking at different types of compounds. Again, we've looked at ionic compounds and molecular compounds. Molecular compounds are a combination of 2 or more nonmetals. Generally speaking, most of the time we're dealing with 2 nonmetals. Ionic compounds are a combination of a metal and a nonmetal, or a combination of a metal and a polyatomic ion, or a combination of ammonium, which is the only positive polyatomic ion we have, and one of those 2 things, nonmetal or polyatomic ion.